Hello, everyone. My name is Matthew Schultz, and I, along with Joseph, Mitchell, and Michael, did our Aerospace Systems Engineering project on Cislunar ISR, in which we analyzed the feasibility of implementing cislunar intelligence, surveillance, and reconnaissance architecture. Here we can see a rough outline of our presentation broken down by section and presenter, and this shows the planned flow of our systems explanation. So beginning with our introduction to Cislunar ISR. Well, the first thing we need to ask is, what is Cislunar ISR? Well, cislunar space can be described as what is seen within the gray area shown on the figure to the right. Everything encompassed by Earth in the Moon's orbit is considered cislunar space. Now that we understand what cislunar is, we take a look at the ISR portion. As mentioned in the title, ISR stands for Intelligence, Surveillance, or Reconnaissance, and currently very few nations have the capability of doing any of these three in space. As more players become capable, however, it is important that we maintain awareness of all missions and help to build proper infrastructure as currently none exist. So why is this all important? Well, lunar and cislunar interest has been steadily increasing over the past few years, and you've probably even seen it in the news recently with missions such as the United States' Artemis missions, India's Moonlander/rover, along with China and Russia, just to name a few. Well, we plan to help facilitate these interests for the United States in multiple ways, such as cislunar exploration for NASA, protection via the U.S. military, such as the Space Force, along with assisting in U.S. commercial interests as seen in companies such as SpaceX. So, in continuing to define the problem of no cislunar architecture, we first take a look at what we plan to achieve in our goals, objectives, and missions, and we analyze what we know our constraints will be. Our biggest goal is to ensure safe travel within cislunar space, and this is done by monitoring incoming and outgoing spacecraft or other space debris, along with promoting an elevated situational awareness. So, how do we do this? Well, by reliably and accurately tracking all known spacecraft, this allows for us to monitor and protect our interests and ensure a safe environment within space. However, not everything is so easily achievable as just me saying it. We anticipate to face constraints in trade offs of affordability and reliability in our spacecraft, along with budget and time constraints for getting the mission going and maintaining. So let's take a look at the current state of the cislunar environment. Most current cislunar systems, outside of the ones locally surrounding the Earth, are primarily for scientific experimentation. One example of this can be seen with NASA's LRO, which currently maps the moon's surface. LRO was originally designed for a 2-year mission, but some 14 years later, it is still kicking. But since it is working long past its expected lifetime, we do not know how long it will last. By implementing our new mega constellation architecture, we can create large scale advancements in many areas, such as updated instruments, faster communications, and redundancies instead of a single lunar orbiter. It is crucial that we take the opportunity to begin advancing this system now, as many competing countries are eager to be the first.
Hello, my name is Michael Zaluki, and I'll be covering our cislunar concept of operations in the next few slides. This is our cislunar concept of operations. Our system of satellites will predominantly operate in cislunar space using near rectilinear halo orbits, NRHO, and lunar orbits. In order to first get our system into cislunar space, our satellites must first lift off from Earth. One of our system's main characteristics, which will be discussed later, is the ability for our satellites to launch on a variety of launch providers. At T-0 on our mission CONOPS, our satellites are launched from Earth into space. During the cruise phase from T+0 to T+6 months, our satellites can utilize a variety of transfer orbits to reach cislunar space. Depicted on our CONOPS is a low energy insertion orbit and a direct injection orbit. After satellites cruised into their planned orbits, they will enter the operations phase. During the operations phase, our system of satellites will utilize their payloads and instruments to provide communication, detection, and inspection of any objects of interest. Objects could be space debris, other satellites, lunar landers, or orbital habitats. With our satellite design, the operational lifetime of each satellite in our system exceeds 10 years in harsh space environments, after which satellites can be disposed of by moving themselves into graveyard orbits or entering heliocentric orbits. This is our ISR satellite's functional flow block diagram. Each satellite will need to perform a variety of tasks throughout its lifetime. Some of the main tasks are highlighted here. communication, encompassing receiving and transmitting data and commands, intelligence gathering, power generation, and pointing control and maneuvering will be some of the main tasks each satellite performs daily. The next slide looks closer at some of the functions required for intelligence collecting. This is a closer look at our intelligence collecting functional flow block diagram. In the center, we start by capturing data with our system sensors. Captured data is then stored on satellite hard drives before being transmitted to another satellite or back to Earth. After transmitting data, satellites can either resume charging their batteries by angling back towards the sun if necessary, or receive commands to locate possible new targets found from the transmitted data. Depending on the orbit for certain satellites, some may maneuver to charge batteries more often than others. The main aspect will be capturing and transmitting data, then locating new targets.
Hello, my name is Joseph Rouse, and I will first be covering the Quality Function Deployment, or the QFD. So, for our purposes, what the QFD was just a systematic approach to fully encompass all the things that our satellite system would contain. This includes the customer requirements, so what the customer wants us to do, the engineering characteristics, and using matrices to allow to compare and contrast all of the things that we could think about in our system. This includes a relationship matrix showing the strength of the relationship between engineering characteristics and customer requirements, as well as things like competitive assessments. So they just show, based off of these requirements or characteristics, what do our competitors have their strengths in. Another thing we use is importance ratings. So it shows how important each customer requirement or engineering characteristic seems to be with a numeric value, as well as target values. So what we target our engineering characteristic values to be.
Hello, my name is Mitchell Smith, and I'll be taking everyone through our system requirements as well as metrics to evaluate some of these requirements and our mission decomposition. Using our customer needs, stakeholder inputs, as well as background research in conjunction with our QFD, we were able to come up with a preliminary requirements diagram to sort of explore how have our requirements related to each other and find derived requirements we could make from some more of the high-level options. As we can see here, we have a large number of high-level requirements as well as some further derived requirements dealing with existing launch capabilities, software to ensure mission continuity, as well as production timelines and cost caps to keep everything affordable and producible in a timely manner. Relating our customer requirements to what we wanted to get out of the system, we determined some engineering characteristics, some being low satellite cost, as well as mission-related functions such as being swapped without constellation interference, relating to high reliability and widespread coverage. We also wanted to emphasize resiliency, and it can be seen in a lot of our requirements as well as how we were designing our system, that our constellation will not have single point failures through the use of a large constellation as well as space qualified hardware. For our mission, it can be broken down into three segments. The space segment, which is composed of the various satellites positioned around lunar orbit and in cislunar space, which have the goal of actually conducting our mission, collecting, storing, and transmitting the data, and is composed of multiple subsystems. The other two segments are the ground communication segment, so the terrestrial ground stations, which will be doing all of our communications with the satellites, as well as the ground support infrastructure, such as our mission processing, command and control, and then the data dissemination that comes down from our satellites. There are multiple metrics that we can use to evaluate different aspects of our mission. Some of these include metrics evaluating the surface area coverage or time to access for various areas of lunar orbit, as well as data latency or communication speed. for the satellite segment. If we look at the ground communication segment, metrics can be used to evaluate the communication availability as well as the production timelines and user satisfactions. Taking a closer look at our coverage evaluation metric, which is the main goal of our mission, for a 100% area coverage of the lunar surface, assuming a 400-kilometer orbit, as well as collection only capable above 15 degrees elevation relative to the lunar surface, it would take a total of 2,459 satellites to cover that entire area. This metric is done through our MBSE parametric tools. So depending on the customer requirements, altitude requirements, or our hardware capabilities, these numbers can be adjusted to better fit the stakeholder and customer needs. This can be further broken down into our total system hierarchy, made once again using MBSE tools, showing the three various segments: our satellite and its respective subsystems, our launch vehicle, as that is a very important part of our ConOps, as well as the ground systems.
Another important thing we did to analyze our system was to generate feasible alternatives for our satellites. One of the main ways we did this was through a morphological matrix. Essentially, this just lists out the different subsystems we have and really is a brain tool and organization tool to show us the different options we can use for these different subsystems. Within these subsystems, we are able to even evaluate single subsystem alternatives. An example of how we would effectively do this is something like a TOPSIS trade study or another qualitative or quantitative trade study. Just for example purposes, we chose the propulsion subsystem to show you how this is conducted. Here you can see the different possible propulsion subsystem choices we could have based off of propulsion devices, such as a cold gas propulsion system or ion, nuclear, hall thrusters, or liquid and chemical. From this, we would create a different way of showing what categories are important to us based off of weights, and then we'd assign values, whether qualitative or truly quantitative, within each one of these choices. Just to show you the rationale for this trade study, we can show you the results table from the TOPSIS trade study conducted, which really just uses some basic mathematical approaches to find a true ranking of each possible option within the subsystem. And from this, you can see that the trade study would say that the ion propulsion system would be the best for our satellite overall. But as you can see, the second place, the hall thruster, is also very close. So once we were able to do this, we were able to rank the top two clear choices while opting out of the rest of the three choices. However, it is noted that based off of the top two being so close, further trade studies would need to be conducted, and it's something that we would definitely do.
Hi, it's Michael Zaluki, and I'll be presenting our preliminary design on the next slide. Although odd-looking, our satellite concept is packed with features. For precise pointing and sensor orienting, each satellite has gyroscopes and ion thrusters, which enable fine pointing and roll control. Our optics themselves also have fine adjustment capabilities to track small objects through the vastness of cislunar space. Each satellite is based on the ESPA platform, which utilizes an ESPA ring docking port, which mounts to ESPA rings to launch dozens of satellites at once. Up to 6 ESPA-class satellites can be launched on one ESPA ring, and multiple ESPA rings can be launched at once. With our modular ESPA design, it allows for easier assembly, enabling shorter system assembly times and getting to the launch pad quicker. Since the ESPA class is standard, any launch provider can accommodate an ESPA ring or ESPA rings. All the design choices highlighted enabled us to hit our customer requirements and keep the price point per satellite low.
So now, coming back to me, let's take a look at our verification and validation plan, or our V&V. So here we can see our preliminary requirement verification matrix and some of our most important requirements. While I won't be going into depth on all of these, we can take a look at our two most important ones and what we deem as a success for them. Taking a look at our efficiency and redundancy requirements respectively, we see that we plan to have our system work for a minimum of 15 years, along with experiencing 0 single point failures. Next, we analyze some of our higher level risks that we anticipate to face, along with what steps we plan to take in order to mitigate these risks. Taking a look at space collisions, we can see that this risk is actually the only one to fall into the red or high risk category, and this is because of the sheer amount of space junk floating around in space around the Earth. However, we plan to implement recognition systems into our satellites to give them a sort of situational awareness of their surroundings in order to avoid debris and make sure that no collisions actually happen.
Lastly, it's Michael Zaluki presenting the summary. To summarize, surveillance of the cislunar region is going to be essential in the near future. Strategically placing satellites in cislunar space will provide advanced benefits for determining and monitoring potential threats and keeping a watchful eye on our own space assets. From our study using stakeholder requirements, we've determined that a satellite mega constellation presents the best solution for our stakeholders' needs for a resilient cislunar architecture.